The web server logs show every request arriving, and it answers all of them with a clean 200 OK. But the users watching their browsers see nothing except a spinning tab, then a timeout. One firewall setting decides whether those replies ever make it back out. Stack lessons here. Let's settle this topic for good. By the end of this video, you'll know exactly when to reach for a security group, when only a network ACL will do, and why mixing up which one is stateful leads straight to wrong answers. This is one of the most frequently tested comparisons in the design secure architectures domain, and it hinges on two ideas most engineers blur together. In episode 8, we built the skeleton of the VPC. You carved out subnets, wired up route tables, and connected the internet and NAT gateways. Route tables answer one scenario: where should this packet go next? But routing never asks whether a packet is even welcome. That's a completely separate job, and it's what we tackle today: the two controls that decide whether a packet is allowed at all. Before we get into how these two controls work, here are the 5 terms that matter most. A security group is a stateful, allow-only firewall that attaches directly to a network interface. One instance, one guard. A network ACL, or NACL, wraps around an entire subnet, and unlike a security group, it can explicitly deny traffic in addition to allowing it. That brings us to stateful versus stateless, the key distinction in this video. Stateful means the firewall tracks a connection and automatically lets the reply through. Stateless means it treats every packet independently, no memory of what came before. An ephemeral-port is the temporary high-numbered port a client selects for a session, and the server's reply travels back to that port. Finally, security group referencing means writing a rule that points to another group's ID, so any instance belonging to that group gets access, without you hard-coding a single IP address. Before we go deep, hold this picture in your head. A packet from the internet has to pass through 2 gates to reach your instance. The first gate is the NACL, sitting at the edge of the subnet. Think of it as the outer perimeter fence around the whole neighborhood. The second gate is the security group, sitting right at the instance's own network interface. That's the lock on the individual front door. The packet must clear both. And crucially, the NACL comes first. If the subnet gate drops the packet, the security group never even sees it. Let's start with the security group. It's a virtual firewall, but it doesn't attach to a subnet. It attaches to an elastic network interface, the ENI. That's why it guards one specific instance rather than a whole neighborhood. The most important limitation to burn-in right now: a security group has allow rules only. There is no deny keyword anywhere in it. It also isn't just for EC2. Anything with a network interface gets one, so that's RDS databases, ECS tasks, even a Lambda function running inside your VPC. And when you create a fresh one, it starts with no inbound rules at all, which means nothing gets in, plus a single default rule that allows all outbound. Here's the property that makes security groups so easy to work with. They are stateful. When you allow a request in, the reply is allowed back out automatically. You never write an outbound rule for it. Allow inbound on port 443, and the response just flows. That one behavior is why security group config stays short, and it's the single most decisive difference from a NACL. Hold on to it. Picture a bouncer at a club who remembers every face they let in. When a guest is approved and walks through the door, the bouncer makes a mental note. Later, when that same guest heads for the exit, the bouncer just waves him out. No separate exit list, no second check. One rule at the door covers the entire visit, both directions. Under the hood, Amazon Web Services calls this memory connection tracking. The firewall records each flow, and it uses that record to let the reply back through without ever consulting your outbound rules. There's a second thing about how security groups decide. They don't march through rules in order. They read all of them together, like a jury weighing every piece of evidence before a single vote. If any rule anywhere across every group attached to that interface permits the traffic, it's in. There's no concept of an earlier rule beating a later one because they're all considered as one combined set. Remember that, because the NACL does the exact opposite. The Amazon Web Services documentation states this plainly. Security groups are stateful. Send a request out from an instance, and the response is allowed back regardless of your inbound rules. Responses to allowed inbound traffic are allowed to leave, regardless of your outbound rules. Read that carefully, because in practice it means the return path is handled for you in both directions. You describe the connection you want once, and the state machine takes care of the rest. Quick recap before we switch controls. A security group lives at the instance level, attached to a network interface. It's allow only, and every rule is evaluated together as one combined set. And it's stateful, so return traffic comes back for free. 3 properties. Lock them in because the NACL is going to invert almost every one of them. Now, the network ACL. Instead of guarding one instance, it wraps an entire subnet, so it protects every instance inside that subnet at once. And here's the capability the security group doesn't have. A NACL supports both allow and deny rules. That deny power is the whole reason it exists. Every subnet is associated with exactly one NACL, though a single NACL can cover several subnets if you like. And the property that defines its personality, it's stateless. It keeps no memory whatsoever of any packet it has already seen. Think of a NACL as a toll booth operator on a two-way road who has complete amnesia. Every car pays a toll in each direction, every single time, and the operator never recognizes a car that came through 5 minutes ago. So a policy that lets cars in does absolutely nothing for cars trying to get out. That needs its own separate policy. This is the crux of stateless filtering. Return traffic is not automatic. If you want the reply to leave, you have to write a rule for it yourself. Here's the other half of the NACL's personality, rule order. Unlike the security group jury, a NACL is a numbered legal code. It reads rules from lowest number upward and stops at the very first match. Watch what happens here. Rule 50 denies traffic from one specific address. Rule 100 allows everything. A packet from that blocked address hits Rule 50 first, matches, and gets dropped on the spot. Rule 100 is never even consulted. And at the very bottom sits an implicit deny, marked with an asterisk, that catches anything no rule matched. Lowest matching rule wins. Full stop. The Amazon Web Services docs put both properties in one passage. Each rule can either allow or deny traffic. There's the deny power. And they evaluate rules in order, starting with the lowest numbered rule, and once traffic matches a rule, that rule is applied and no further rules are checked. 2 behaviors in 2 sentences. It can deny and it stops at the first match. That's the opposite of the security group on both counts. Let's line them up side by side. The security group works at the instance level, on the network interface. The NAL works at the subnet level. The security group is allow only. The NACL does both allow and deny. The security group evaluates every rule together. The NACL goes in numbered order and stops at the first match. And the big one at the bottom, the security group is stateful, so return traffic is automatic, while the NACL is stateless, so you must permit return traffic explicitly. 4 rows, and every single one is a mirror image. Quick recap on the NACL. It's subnet level, 1 per subnet. It handles both allow and deny, ordered strictly by rule number with first match winning. And it's stateless, which means you permit both directions of every flow yourself. That last point is exactly where the outage from our opening comes from, so let's go see it happen. Here's the exact sequence that makes stateless filtering bite. The client's browser opens a connection to port 80, but it picks a random high-numbered source port for itself, say 54,321. Your inbound NACL rule allows port 80, so the request sails in. The server processes it and sends the response back to that source port, 54,321. Now the NACL checks its outbound rules for traffic headed to that port. And if you never added a rule covering that high range, the implicit deny catches the reply and drops it. The request arrived, the server answered, and the answer died silently at the subnet edge. Think of it like phoning a company. You dial their published main line, that's port 80, and that's your inbound rule. But the receptionist gives you a one-time callback extension, some random number between 1,024 and 65,535 that exists only for your call. When they ring you back, they use that temporary extension, not the main line. So if a NACL is a building security desk logging every outbound call, it has to permit that entire range of temporary extensions, or the callback never reaches you. That temporary number is the ephemeral-port. The fix is one line. Add an outbound NACL rule allowing TCP ports 1024 through 65,535. Different operating systems use different subranges, but that broad window covers all of them safely, and it's what Amazon Web Services recommends. Here's the contrast worth remembering. A security group would have needed nothing at all, because it's stateful. The reply to that ephemeral port was always going to be allowed automatically. Stateless is the entire reason you need that extra rule. This is what the outage actually looks like from both sides, and it's maddening. The client connects fine, sends its request, and then just hangs until it times out after 30 seconds having received 0 bytes. But look at the server log on the next line. 200 OK, served in 4 milliseconds. The server did its job perfectly. The reply simply never made it back across the subnet boundary. The symptom looks exactly like a routing problem, which is why engineers can burn hours chasing the wrong thing before they check the outbound NACL rules. So when do you genuinely need a NACL instead of a security group? Here's the decision rule that answers most exam questions on this topic. If you must explicitly block something, a specific address, a whole range, a particular protocol, it has to be a NACL. Security groups cannot deny, period. The moment a scenario says block or deny or stop this range, your answer involves a network ACL. Let's make that concrete. Megacorp security team spots a range of addresses, 198.51.100/24, hammering their public web subnet with automated scans. They want everyone else in, but that range out. Could they do it with a security group? No, there's simply no deny keyword, so no matter what allow rules exist, there's no way to carve out an exception. The NACL solves it instantly. They add a deny rule at number 50 for that range, placed below the broad allow at 100. Because evaluation stops at the first match, the attacker's packets hit rule 50 and die before rule 100 is ever reached. And because a NACL guards the whole subnet, every instance is protected the moment that rule lands. The documentation could not be more blunt about this. For security groups, you can specify allow rules, but not deny rules. 6 words. If an answer choice claims a security group is blocking a specific IP range, that answer is wrong on its face. The capability does not exist. This one sentence resolves a whole category of questions. There's a second reason to reach for a NACL. It's a safety net. Because it covers every instance in the subnet regardless of that instance's security group, it protects even the machine that got launched with the wrong group by mistake or through an automation slip. A security group simply cannot do that. If an instance never got the right group, the security group protection isn't there. The NACL is Amazon Web Services describes this exactly. Use security groups as your primary control and use NACLs as coarse-grained subnet guardrails for defense in depth. Here's a subtle one with real incident response consequences. Say an attacker has an active session into an instance, and you rip out the security group rule that allowed them in. You'd expect the session to drop. It doesn't. Remember connection tracking? That flow was already tracked, so it keeps flowing until it naturally times out. To cut them off this second, you apply a NACL deny for the attacker's address instead. Because the NACL is stateless, it judges every packet fresh and drops the very next one, no matter that a session was already established. For instant containment, the NACL is your tool, not the security group. Now let's swing back to security groups for their most powerful trick, which NACLs can't touch. In a security group rule, the source doesn't have to be an IP range. It can be the ID of another security group. When you do that, the rule means allow traffic from any member of that group. And read this part carefully, because it trips people up. It does not import the other group's rules. Only membership matters. If an instance belongs to the referenced group, its traffic qualifies. And any new instance that joins later is covered automatically. No rule change needed. This is where referencing pays off. A clean 3-tier chain with not one IP address in it. On the left, the load balancer group allows port 443 from the whole world. In the middle, the application group allows 443, but only from the load balancer group as its source. On the right, the database group allows port 3306, only from the application group. The database is unreachable from the internet because nothing on the internet is a member of the application group. And when autoscaling adds 10 more app servers, they inherit the group and are instantly allowed. No rule ever changes. Picture a corporate floor where the door doesn't list every employee's name. Instead, it just says, anyone with a blue app tier badge may enter. That blue badge is the security group ID, and holding it is what grants access. When new hires join the app team, they're handed a badge automatically and walk right in. Nobody edits the door policy. When people leave, they lose the badge and lose access. The policy never changes even as the team grows or shrinks. That's why referencing scales effortlessly and IP lists don't. There's an elegant variant of this, a group that references itself. Megacorp puts all 14 of its microservices into one security group, then adds a single inbound rule allowing all traffic from that same group as the source. Now, any microservice can reach any other microservice on any port freely. That's your east-west mesh inside the tier. But nothing from outside the group gets in without an explicit extra rule, so your north-south boundary stays strict. One self-referencing rule buys you a whole internal service mesh with a hard perimeter around it. Here's the full official comparison, and it's worth pausing on if you want it burned in. Security group operates at the instance, NACL at the subnet. Security group is allow only. NACL does allow and deny. Security group weighs all rules before deciding. NACL takes them in numbered order. First match wins. Security group return traffic is automatic. NACL return traffic must be explicit. And the last row we haven't stressed yet, a security group source can be another group's ID, while a NACL only understands raw address ranges. That final row is exactly why tiered architecture is stored in security groups, not NACLs. So here's the decision in one clean tree. Ask yourself, do I need to explicitly block a specific address or range? If yes, you need a NACL. It's the only control that can deny. If no, and you want instance-level precision or the ability to reference a group as your source, you want a security group. But notice the line at the bottom, because it's the real answer for Megacorp. Most well-designed VPCs use both. They aren't rivals, They're layers. Tight security groups on your instances, plus a NACL deny layer at the subnet edge for known bad ranges. If you remember nothing else from this entire video, remember this one line. Security groups are stateful and allow only. NACLs are stateless and can deny. Say it a few times until it's automatic, because a huge share of the confusion around VPC security comes from swapping those two properties. Get this line right, and the answers fall into place. Let's carry these forward. First, stateful versus stateless is the decisive difference. It settles most questions on its own. Second, only a NACL can deny, so if you must block an address, it's a NACL every time. Third, because NACLs are stateless, they need an outbound rule for the ephemeral port range, 1024 through 65,535, or replies vanish. Fourth, reference a security group by its ID to build tiers that scale without ever touching an IP list. And fifth, remember the ordering. Traffic clears the NACL at the subnet before it ever meets the security group at the instance. Now let's put all of this to the test with 5 quick questions. Question 1. A team needs to block all traffic from a malicious IP range reaching their public subnet, while still allowing every other internet visitor in. Which control can do this? A network ACL deny rule. B, a security group inbound deny rule. C, either one will work. Or D, a route table entry to black hole the range. Lock in your answer before I give it away. The right call here is A. A security group is allow only. There's no deny keyword in it at all, which rules out B and C. A route table controls where traffic goes, not whether it's permitted, so D is out. Only a network ACL can express an explicit deny for that specific range while leaving everyone else allowed. Question 2. A web server security group allows inbound port 80, but clients request timeout with 0 bytes received, even though the server logs show clean 200 OK responses. The subnet has a custom NACL with only an inbound allow for port 80. What's the most likely cause? A, the route table has no path to the internet gateway. B, the security group is missing an outbound rule for port 80. C, the security group is stateless and drops the return traffic. Or D, the NACL is missing an outbound rule for ephemeral ports. Think about which control is stateless here. If you said D, well done. The NACL is stateless, so the server's reply headed to the client's ephemeral source port somewhere in the 1024 to 65,535 range needs its own outbound rule, and it's missing. B is wrong because the security group is stateful and handles its own return traffic. C reverses the property. Security groups are stateful, not stateless. And the server logs prove routing works. So A is out. Question 3. An RDS database in a private subnet should accept traffic only from your application tier, which is constantly scaling in and out with autoscaling. What's the most scalable, maintenance-free rule for the database's security group? A, list each application server's private IP. B, set the inbound source to the application tier's security group ID. C, add a NACL allow for the application subnet's range. Or D, open it to the world and let the NACL filter. Got your pick? Let's see. This one is B. Reference the application tier security group ID as the source, and every current and future member is covered automatically. Autoscaling can add or replace servers all day and no rule ever changes. A breaks the moment an instance is replaced with a new IP. C is coarse and can't track group membership. And D throws the door wide open, which is the opposite of least privilege. Question 4. An engineer removes the inbound port 22 allow rule from an instance's security group to kill an attacker's live SSH session, but the session stays up. Why and what should they do instead? A. The change just hasn't propagated, so wait. B. Connection tracking keeps the established session alive, so apply a NACL deny to cut it immediately. C. S. Ignore security groups, so reboot the box. Or D. The outbound rule still allows port 22, so remove it. Run the decision rule from earlier before you answer. It has to be B, and here's why. Security groups use connection tracking, so a session that's already established keeps flowing until it times out, even after you pull the allow rule. To cut it instantly, apply a stateless NAL deny for the attacker's address. It drops the very next packet regardless of connection state. Waiting in A won't help. SSH does respect security groups, so C is wrong, and D misunderstands how stateful return traffic works. Question 5. An inbound NA call has Rule 50, denying TCP from one address, and Rule 100, allowing all TCP from anywhere. What happens to an inbound packet from that denied address? A. It's allowed because the broad allow at Rule 100 takes precedence. B. It's allowed because security groups override NACL denies. C. It's denied because Rule 50 matches first and evaluation stops. Or D. Both rules are weighed and the allow wins as a tiebreaker. Pause here if you want more time. The answer is C. NACLs evaluate rules from the lowest number up and stop at the first match. Rule 50 is lower than Rule 100, so the deny matches first and the packet is dropped before Rule 100 is ever consulted. There's no precedence for the broad allow. NACLs don't get overridden by security groups this way, and unlike security groups, there's no way everything tiebreaker, first match wins. That finishes VPC traffic control. Security groups versus NACLs. Subscribing is genuinely what keeps these lessons free and in front of new students, so if you can, please do. Tell me in the comments what helped most. If there's a certification you'd love a series on, drop it below. Your requests decide what's next. And any thoughts on improving the pace or the visuals? I'm listening. Thanks for watching the Cloud Architect Path.